the quantum awakening. Recent breakthroughs in quantum technology have brought humanity to the threshold of one of the most revolutionary innovations in modern history, the creation of an ultra-secure quantum internet that could fundamentally transform communication, computing, and cybersecurity. In new research published in prestigious journals like Nature Communications and Nature Materials, scientists have overcome major obstacles that had hindered practical applications of some of the most bizarre yet promising aspects of quantum physics. By finding ways to reliably store entangled quantum particles or individually generate and control the polarization of single photons, researchers now possess key capabilities needed to encode, transmit, and safeguard data using the principles of quantum mechanics. Although a full-fledged quantum internet could still be years away, these discoveries provide a glimpse of the strange new quantum world that awaits us, bringing us to the cusp of an unhackable communications network that runs at unbelievable speeds. As we stand at this revolutionary precipice, it's worth understanding the science powering this quantum awakening and what's shaping the strange new landscape of our quantum future. Entangling photons at telecom wavelengths. One of the major challenges in building quantum networks is transmitting quantum information over long distances. Quantum phenomena like entanglement allow seemingly magical effects, such as linking the properties of particles no matter how far apart they are, but these effects are easily destroyed by interactions with the environment. For example, entanglement enables secure communication through quantum key distribution. Here, entangled pairs of photons are shared between two parties, and then the polarization or other properties of each photon are measured to create an encryption key. However, entanglement breaks down over long distances in optical fibers due to signal loss and noise. One way to tackle this issue is by using quantum repeaters, devices that extend the range of quantum networks by storing the fragile quantum state of photons in matter-based quantum memories. This allows the entanglement between photons to be maintained over longer distances by repeatedly measuring, storing, and retransmitting the quantum signal. For quantum repeaters to be effective, though, they need to be compatible with modern telecommunication networks. This means operating at standard telecom wavelengths around 1.55 microns and being able to integrate into real-world fiber infrastructure. Recent research from Nanjing University represents a huge leap forward in this regard. The team developed a system that can store entangled photons at telecom wavelengths using rare earth ions embedded in a crystal. Critically, their storage system is integrated with a photon source that can generate entangled photon pairs, also at 1.55 By combining these capabilities and leveraging a special magnetic field to extend the storage lifetime of the quantum memory, the researchers achieved the longest storage time of any quantum repeater system to date, around 2 microseconds, nearly 400 times longer than previous experiments. This could pave the way toward mass-producing efficient, telecom-compatible quantum repeaters, a pivotal milestone on the path toward continent-spanning quantum communication. Generating and polarizing single photons on demand. Moving, storing, and measuring individual quanta of light, called photons, is another essential capability for quantum networking. Photons are ideal information carriers for transmitting quantum data, but producing individual photons and controlling their quantum properties has proven extremely difficult. However, researchers at Los Alamos National Lab recently demonstrated a new technique that can generate single photons on demand, while simultaneously controlling an inherent quantum trait known as polarization. This 2-in-1 photon source vastly simplifies development of quantum photonic devices compared to previous approaches. Their method leverages unique nanoscale physics between layered semiconductor materials to emit individual photons with circular polarization as electrons cascade down into nanoscale depressions in the material. Varying the depth and shape of these indentations provides precision control over the photon polarization. This technique is also compatible with existing methods to modulate polarization encoding, couple photons into miniature photonic circuit waveguides, and interface the photons with quantum memory systems. Together, these capabilities supply all the constituent parts necessary for building systems that can generate, store, process, and transmit quantum information. The simplicity and reliability of this new polarized photon source could rapidly accelerate research and development of quantum communication channels. And notably, the team highlights its advantages for enabling quantum key distribution, QKD, the ultra-secure method of encrypting data with quantum properties that underpins visions of an unhackable quantum internet. By encoding information in quantum states like photon polarization, QKD can in principle allow two parties to communicate with absolute privacy. This is because fundamentally quantum information cannot be copied or measured without detection, owing to its fragile and ephemeral nature. Intercepting and extracting data from a quantum signal without being caught is provably impossible. The quantum awakening with QKD as a virtually unbreakable encryption method, a full-fledged quantum internet could revolutionize communication security and provide theoretically uncompromisable data transmission. And tools like polarized single photon sources and quantum repeaters now offer tangible building blocks to start realizing this vision and constructing long-range quantum networks. But the implications stretch even further. By linking quantum processors into a quantum internet architecture, we open the door to the quantum awakening, a transformation and expansion of computing power unlike anything ever seen before. Owing to counterintuitive quantum phenomena like superposition and entanglement, quantum computers can inherently solve certain problems exponentially faster than even the most advanced supercomputers today. They utilize quantum bits or qubits that can perform calculations in a huge combinatorial space, evaluating all possible solutions simultaneously. Yet high quantum processing demands that large numbers of qubits connect and entangle, an effect that rapidly degrades over distance. Quantum networking would enable quantum computers to scale radically by linking distributed nodes into unified computational cluster. Even just a few nodes magnifies their power enormously compared to isolated machines. With transformative quantum applications spanning from chemistry to finance to machine learning and materials science, some estimate that quantum computers could produce economic impacts over $850 billion annually within about a decade. The quantum internet promises to accelerate this timeline by providing the critical communication backbone, enabling distributed quantum processors to function in harmony. Furthermore, when integrated into the classical internet we use today, quantum networks open the possibility for perfectly secure communication channels that can transmit staggering amounts of data at light speed. Terabit per second information rates could become commonplace for quantum links, about 10,000 times faster than household broadband today. The quantum horizon, unfettered machine learning, revolutionary drug design platforms, unhackable global communication networks. The strange science powering this quantum awakening seems almost otherworldly, yet guides our technology to unprecedented heights. By mastering quantum states that exhibit almost magical, if ephemeral, effects, researchers now stand at the horizon of a computing and communication revolution, with recent advances bringing robust capabilities for transmitting and manipulating quantum information. The final steps toward this quantum future appear within reach. Of course, realizing the full vision of an interconnected quantum web requires intensive further engineering to build out and network quantum hardware across global scales. But these discoveries usher in a new phase, the phase where quantum technology is maturing from untamed science toward transformational, real-world applications. Much like the early days of the classical information revolution, we are just now glimpsing the life-changing potential blossoming out of applied quantum science, a power we have only begun to grasp. But make no mistake, our quantum awakening is arriving, and it promises to again radically reshape the fabric of society in ways both subtle and profound. With the coming quantum age, the impossible is now inevitable. Visit our website at www.ultraunlimited.com to learn more about the latest quantum advancements driving humanity forward.